All right. So today we are going to be talking about positive feedback op-amp circuits. Let me change this color. So, okay. So I'm going to pull up LT Spice here really quickly, and I am going to run a simulation. So the first thing that I want to show you guys is our simple comparator. So I'm going to change this to just VN really quickly. And I'm going to run our simulation. And we're going to look at V in and V out. And we can see quite easily that our output voltage goes low whenever V in is less than 3 volts. And our output voltage goes high whenever V in is greater than 3 volts. So we have a simple non-inverting comparator. So what I'm going to do now is I'm going to introduce some noise on my input signal. I've done this by putting 2 voltage sources in series. So down here, we have our voltage source, our regular input voltage that just ranges from -10 to +10. And then on top of that, I've added a simple white noise generator. And so the node here that has these 2 voltages added together is labeled as Vn plus N. So I'm just going to put plus N here and rerun my simulation. We're going to look at our input signal. So it's a sinusoid with a small amount of noise added on top, which is exactly what I wanted. And when we look at our output voltage, now we have something a little bit different. So I'm going to kind of zoom in here. We're going to take a better look at what's going on between 0 seconds and 0.1 seconds. And I'll make that just 10 milliseconds. So in this zoomed in bit, we can see that our output signal changes rapidly from its low state to its high state, and then a moment later goes back down. A little bit later, we have a similar situation before it finally stays high. So what's happening is that when we have noise that occurs close to our reference voltage, because the open loop voltage gain of this circuit is so large, it causes the output to change states very rapidly. So it's doing the comparison that we're looking for, but because we're not comparing things to a stable signal, we see that our output has some type of oscillations. So in order to prevent these oscillations from occurring, we can employ a technique called positive feedback, which we talked about in our last class meeting. Let me rerun the simulation real quick. So down here in our schematic diagram, we can see that we have a 10 kilo ohm resistor that forms our feedback path, which connects our non-inverting input terminal to our output terminal. And so I'm applying that same input signal plus noise to this node. So we have our input signal plus noise. When we look at our output, we have a nice stable output. Now, one thing to note here is that our input signal transitions from low to high now somewhere in the ballpark of 7 volts, and it transitions from high to low somewhere in the ballpark of 1.4 volts. So even though our reference voltage is still 3, because we're just using this signal as our reference voltage applied here, we now effectively have comparison to 2 different voltages. So what I'm going to do here is I am going to draw this circuit for you guys in a general form, and then we are going to figure out how to mathematically determine where these transition points are as a function of our circuit parameters. So the circuit that I implemented in ELEN Spice is an example of a non-inverting Schmidt trigger. Let me write that down. And with a non-inverting Schmidt trigger, we have our simple op-amp circuit. So here's our op-amp, here is our non-inverting terminal, our inverting terminal. So let me just label this V plus, V minus respectively. Here's V out. So again, we're going to have our supply voltages, VCC plus and VCC minus. As I mentioned a moment ago, we are going to have positive feedback. So I'm going to place a resistor, which I'm going to call R2, between the non-inverting input terminal and the output terminal. I am going to place a resistor R1 between the non-inverting input terminal and the actual input signal. So this is where we're going to apply V in. And then I'm going to apply my reference voltage here at the inverting input node. So we are going to analyze this circuit by using the practical op-amp model. But before we do that, we are going to make a few quick assumptions here that will aid in our analysis. So the first assumption that we are going to make, let me write this down. Excuse me. The first assumption that we are going to make is that the input resistance of the op-amp is much, much greater in size than the resistor values R1 and R2. So typical values for the input resistance of an op-amp, once again, are somewhere in the ballpark of a mega ohm, and we know that we should be biasing op-amps with kilo ohm size resistors. So Rn is at least 1,000 times larger than R1 plus R2, so we should be good to go there. Additionally, our output resistance should be significantly smaller than R1 and R2. Excuse me. So since the typical output resistance for an op-amp is on the order of tens of ohms or smaller, and we use kilo ohm size resistors to bias, once again, this assumption is valid. Lastly, we are going to assume that our open loop gain, AVOL, is large. And so by this, I mean that our open loop gain is probably 1,000 or more, which for most op-amps in an open loop configuration, we're usually dealing with tens to hundreds of thousands of volts per volt in voltage gain, if not even larger. So all of these things should be true for practically any op-amp circuit that's biased with kilo ohm size resistors. All right, so I'm going to redraw my circuit using the practical op-amp model. So once again, I'm going to start with just the practical op-amp model by itself. Excuse me. So this is my non-inverting input terminal. Here is my input resistance Rn. This is my inverting input terminal. Over here, I'm going to have my practical voltage source. So this is my open loop gain times my differential voltage. So while I'm at it, I'll define my differential voltage over here, which will be nothing more than the voltage seen between our non-inverting and inverting input terminals. Here is my output resistance, R out, like so. And here is that ground rail that's effectively common to everything. And let me explicitly ground things here. All right, so that's my op-amp. Now I'm going to make my external connections. So my output signal is just measured at the output terminal, so it's an open circuit voltage here. My reference voltage is applied between my inverting input terminal and ground. So this is Vref. I have my feedback resistor that connects my non-inverting input to my output. So I'm going to put that guy up here. I have a resistor R1 connected between my non-inverting input terminal and my input signal. And so now my input signal is placed between this leg of the resistor and ground, like so. Okay, so let's put our assumptions into place here. Okay, so if Rn is much, much greater than the resistors R1 and R2, then I can say that the current flowing through Rn is very, very small, approximately 0 amps, right? Realistically, this current is somewhere in the ballpark of nanoamperes in size. But for our intents and purposes, when we're going to be dealing with milliamp scale currents flowing through resistors R1 and R2, a nanoamp of current is 1,000,000 times smaller. So that's going to be close enough for us to call it 0. So since there is no current flowing through our input resistance, that effectively means that our voltage VD here is going to be 0 volts, which in turn means that our reference voltage Vref is what's seen at the non-inverting input terminal. Okay. So what we're going to do now is we are going to, excuse me, write a Kirchhoff's current law equation where we are going to add, let's do it in pink. This current plus this current together, okay? With the understanding that the current that branches off and flows to the right is approximately 0. So when we apply Kirchhoff's current law at our non-inverting input. What we will get is Vref minus Vn divided by R1 plus Vref minus Vout divided by R2 is equal to 0. Now I'm just going to do some simple manipulation here. I'm going to leave all of my Vref terms on the left-hand side, and I'm going to move my Vn and Vout terms to the right-hand side. So with my Vref terms on the left-hand side, what I could simplify this to be would be Vref times 1 over R1 plus 1 over R2 will be equal to Vn over R1 plus Vout over R2. This term right here is nothing more than R1 in parallel with R2, the reciprocal of that, right? So I can multiply through by R1 in parallel with R2 to clear that term. And what that's going to leave me with, if my stylus will write, is Vref will be equal to R2 times R1 plus R2 multiplied by Vn plus R1 over R1 plus R2 times Vout. This is my characteristic equation for my non-inverting Schmidt trigger. So this is the equation that governs how this circuit is going to behave. It might seem a little bit odd, so let me explain what I mean, okay? So this circuit has what are called trigger limits. And the trigger limits are those transition voltages that I was mentioning earlier when we looked at the circuit. In fact, let me bring up LT Spice here. So looking at this picture, I can see that I have one transition voltage that occurs somewhere in the ballpark of 7 volts. And then I have another transition voltage that's occurring somewhere over here in the ballpark of 1.5 volts or so, right? Just based on looking at the graph, we'll find out the numbers here in a moment, right? So I'm going to define two different terms now. We are going to have an upper trigger limit and our upper trigger limit is defined as the input voltage which causes V out to change from VCC minus to VCC plus, right? So it's what the input voltage that causes the output to switch from its low state to its high state, okay? So for the circuit that we were just dealing with, we know that R1 was 3 kiloohms. R2 was given as 10 kiloohms. Vref was 3 volts. VCC plus was 10 volts. And VCC minus was negative 10 volts. So we can calculate our upper trigger limit voltage by saying that Vref will be equal to R2 over R1 plus R2 times V upper trigger limit plus R1 divided by R1 plus R2 times our output voltage. We want our output voltage to go from low to high, so we're going to put VCC minus into our equation right here. And now I'm going to substitute in my numbers, right? So we're going to have 3 volts will be equal to 10 kiloohms over 10 plus 3 is 13 kiloohms times our upper trigger limit voltage that we're trying to solve for, plus R1, which is 3 kiloohms, times R1 plus R2, once again, 13 kiloohms, times VCC minus, which is negative 10 volts. And if we rearrange this thing, what we'll find is that our upper trigger limit, VUTL, comes out to be 6.9 volts, which agrees pretty well with what our graph showed us. So now let's define our lower triggers. Once again, this will be the input voltage which causes V out to change. But now we're going to see it transition from, sorry, that says frau, not from, VCC plus to VCC minus. So this is the input voltage that causes our circuit to transition from a high output state to a low output state. So using our characteristic equation, we're just going to be doing this. Vref will be equal to R2 times R1 plus R2 times VLTL for lower trigger limit plus R1 over R1 plus R2 times VCC plus, because we are starting with our output high. If we substitute in our numbers, what we are going to have is 3 volts will be equal to 10 kiloohms over 13 kiloohms times our lower trigger limit voltage plus 3 kiloohms over 13 kiloohms times VCC plus, which was 10 volts, and solving for VLTL, we find that this voltage is 0.9 volts. So let's go back to our LT spice diagram here really quickly. And we're going to look at this graph from a different perspective, much like we did in class on Wednesday. Instead of plotting this as a function of time, I'm now going to plot this signal as a function of input voltage. So I'm going to look at V at Vn as a signal I'm plotting against. And I get this funny looking curve here. This is what would commonly be called a hysteresis curve. It actually, in some ways, shows that this circuit has, if we were dealing with a magnetic circuit, we would call it memory, but because this isn't a magnetic circuit, I'm going to call this latching, okay? So let me explain how we would read this graph, okay? So let's say that our input signal starts over here at negative 10 volts. Our output stays low all the way until we reach this point, at which point we have hit our upper trigger limit. The output swings up and then it stays high all the way until we hit 10 volts. When we come back down, so starting at positive 10 volts, our output is going to be at VCC plus all the way until we hit our lower trigger limit, at which point it's going to swing low, and then it's going to stay low all the way down to negative 10 volts. And then that cycle just repeats itself over and over and over. This little triangular bit here is just an artifact of there being multiple passes of this input signal passing through. But we're really just interested in where these vertical lines occur, right? So this vertical line is occurring at an X of 6.7 volts, which is pretty close to the 6.9 volts that our model tells us that we should have. And this one occurs at 0.98 volts, which once again is pretty close to where our model tells us where our lower trigger limit should occur. The discrepancy here is because we are ignoring any current that can flow through the input resistance of the op amp, okay? So this just gives us a good design approximation. It's not going to be exactly spot on all of the time, but it's going to be pretty close, which is good enough for me for when we're trying to design things, okay? So this is how you determine the approximate upper trigger limit and lower trigger limit of a Schmitt trigger circuit, okay? Or excuse me, an non-inverting Schmitt trigger circuit. Okay. We've shown that our mathematical model that we have developed gets us answers that are pretty well agreeable with our simulation. So now let's look at an inverting Schmitt trigger circuit. So in an inverting Schmitt trigger circuit, we are literally going to have the exact same circuit, except that where we apply our reference voltage and where we apply our input voltage have changed places, okay? So starting with my op amp, here is my non-inverting input terminal, here is my inverting input terminal. So I'm going to go ahead and label those nodal voltages. Here's my output terminal and its voltage. Up here, I have VCC plus. Down here, I have VCC minus. Once again, I'm going to have positive feedback. So I'm going to have some resistance R2 connecting the non-inverting input terminal to the output terminal. So we'll put R2 here. I'm going to have some resistor R1 between the non-inverting input terminal. And now instead of applying my input signal here, I'm going to apply my reference voltage here. And my input signal instead gets applied at the inverting input terminal. So instead of redrawing this circuit and all of that kind of good stuff, using the practical op-amp model, I am going to ask us to make a little bit of an intuitive leap here. Let me scroll up so you can see the equation. So I would argue that for a non-inverting Schmidt trigger, excuse me, if we replace V reference and Vn where they are in this equation, we will get the exact same result as if we had analyzed the circuits, because the only difference that happened to the circuit was we switched where Vn and Vref were placed. So using that line of reasoning, I am going to say that the characteristic equation for this circuit will be Vn is equal to R2 over R1 plus R2 times Vref plus R1 over R1 plus R2 times V out. Our definition for upper and lower trigger limit are exactly the same. Meaning that the upper trigger limit is when the input voltage, when our output signal goes from VCC minus to VCC plus. So from that, we could say that VUTL is just going to be R2 over R1 plus R2 times Vref plus R1 over R1 plus R2 times VCC minus. And our lower trigger limit is going to be the exact same equation, but we're going to replace VCC minus with VCC plus. If we go into LT Spice, and we swap where we're applying Vref and Vn, like so, and simulate, we get an inverted version of our Schmidt trigger response, right? So now we are going to be high until we hit our upper trigger limit, at which point we swing low, and then we stay low until we hit our lower trigger limit, at which point, actually, hold on, sorry. We're going to stay low, or excuse me, we're going to stay high until we hit our lower trigger limit, at which point we go low. We're going to stay low and come back around, and we're going to switch to high when we hit our upper trigger limit, like so. So if we plugged in the numbers that we have, just for the sake of argument here, we can see that one of our trigger limits should be 0 and the other one should be about 4.6 volts. If we plugged in our numbers, so R2 is 10, so that's going to be 10 over 13 times 3 plus 3 over 13 times VCC minus, which was negative 10. I got a syntax error. Give me a second. Multiply there. 0 volts, and 10 over 13 times 3 plus 3 over 13 times positive 10, 60 over 13, sorry, 4.61 volts. So pretty much exactly what we would expect based on the graph that we had. So once again, the only analysis that we really, or actually, let me rephrase that. We didn't even need to do any analysis to figure out the behavior of a inverting Schmidt trigger if we understood how a non-inverting Schmidt trigger worked, because we're simply changing the position of those two voltages. All right, so before I move on to the last circuit that we are going to look at today, are there any questions? All righty, so the last circuit that we're going to look at is what's called an astable multi-vibrator circuit. There are multiple different ways to implement this circuit. We are going to be looking at the op-amp configuration since we're dealing with op-amp circuits. So this is the op-amp multi-vibrator circuit, or which we'll see momentarily, a simple way to make an oscillator or timing circuit. So once again, we're going to start with our op-amp. Here is our inverting input terminal. I'm going to put it on top. You'll see why in a moment. Here's our non-inverting input terminal. Here we have our positive supply voltage, VCC plus. Down here, we have our negative supply voltage, VCC minus. We label things here. So this is going to be V plus, V minus, V out. Here is my feedback resistor, which I am going to call, in this case, R1. Then I'm going to have a resistor R2 connected like so to ground. So I have positive feedback, and then I also have this kind of voltage divider-esque thing going on here between R1 and R2. I'm also going to have a negative feedback path. Okay. So this circuit, while it does display, or it does have both positive feedback because we are tying our non-inverting input terminal to our output terminal through that resistor R1, and it's going to have negative feedback because we're about to tie our inverting input terminal to our output terminal through this resistor R. Because it contains a positive feedback path, it is pretty much going to behave like a positive feedback circuit. Okay. The last component that we are going to have here is a capacitor. I'm going to call C, and I'm going to ground this bottom leg of the capacitor. Okay. So I'm going to label the voltage at this node VC. So this is my capacitor voltage with respect to ground. And I am going to label the voltage at this node Vref, because the voltage applied at this node is effectively serving as a reference voltage for this circuit. Okay. So how this thing works is a little bit tricky. So we're going to talk our way through it and then supplement that talking with some graphs. So the first plot that I am going to look at and talk you through, the vertical axis is going to be voltage, and then the horizontal axis is going to be time. And this bottommost graph is going to be how we look at V out as a function of time. So let me just label this one. V out as a function of time. This one up here is going to give us Vc as a function of time and Vref as a function of time. And I'm going to use two different colors so that we can understand what's going on. Okay. So to start, we are going to assume that Vc is equal to 0, or let me write this better. Vc of 0 is equal to 0 volts. And we are going to assume that V out of 0 is equal to our positive supply voltage. Okay. So that means that Vc, which I'm going to do in purple, is going to have a starting point here. And V out, which I will do in green, will have a starting point, let's say here. And just for the sake of argument, I'm going to label this point as VCC plus, and I'm going to label this point as VCC minus. Okay, so these are our initial conditions for our system. Okay, so VC starts at 0 volts. Since V out is VCC plus, that means that V reference is going to be V out times R2 over R1 plus R2, because we have a simple voltage divider circuit, right? Where we are assuming that, actually, let me write this down. If Rn is much, much greater than R1 and R2, then V reference will be V out times R2 over R1 plus R2, because we have established this bias point using a voltage divider at the output. Okay, so if V out starts as positive, then Vref will be a positive voltage. Okay, so I'm just going to start Vref here in red as some positive voltage, and I'm going to label things here. So Vref is going to be in red. Vc is going to be in purple. The only signal on my bottom graph is V out, so that's going to be the green thing. Okay. So with this reference voltage, as some positive voltage, let's look at what's going to happen to the capacitor. Okay. So if Vc is at 0 and V out is at 10 volts, what we're going to see is that current is going to flow through that resistor R. And that current flowing through resistor R is going to cause our capacitor to charge at a rate determined by R times C, because we have an RC circuit. R times C is the time constant for this thing, right? So what we're going to see is that our capacitor is going to charge up to a certain point, okay? Now, once our capacitor voltage hits what our reference voltage is, we will find that our output voltage is going to swing to VCC minus, right? So our reference voltage is going to be positive and stay positive until the capacitor voltage meets it. And we are going to see that our output voltage stays positive until, once again, that capacitor voltage meets the reference voltage, at which point our output voltage changes states. So it's going to swing to negative. When our output voltage swings negative, our reference voltage also has to swing negative because they're tied together with a voltage divider circuit. And now our capacitor is at a higher potential than V out. So our capacitor is going to start discharging through resistor R. And so we're going to see that it discharges over time, like so, dependent on that RC time constant. When our capacitor voltage hits our new negative reference voltage, our output voltage swings back up and the cycle starts again. And so this just repeats over and over and over. Our capacitor voltage is always chasing the reference voltage, and the reference voltage is always a scaled version of our output voltage. So we'll just draw this. So what we wind up getting is an oscillator circuit. So our output voltage is changing from VCC plus to VCC minus and back at very regular intervals that are defined by how long it takes our capacitor to discharge. So this is a very simple clock circuit that we can tune by using different component values. So let's take a moment here and simulate this circuit. So I'm going to close out this and open a new schematic because I don't have a version of this saved for whatever reason. So we're going to start with universal op amp 2. Throw that guy smack in the middle. I'm going to set up my power supply voltages. Those are the only voltages that I need. One thing that I didn't mention, but you guys may have noticed, there is literally no input voltage in this system. So we don't do anything to excite it. It just runs due to effectively thermal energy stored in the capacitor. So voltage. Let's tie these together. Ground node here. Sorry, I didn't mean to scroll that far. Let's make this 10 and minus 10 effectively, just for the sake of argument, doesn't particularly matter. This is our positive supply voltage terminal that gets applied to our positive supply voltage pin. Here is our negative supply voltage that gets applied to our negative supply voltage here. And now I'm going to start wiring this thing up. So right now I'm just running everything as wires, and then here in a moment, I'll start putting in the actual resistors and all that kind of good stuff. So let's see. So this is going to be R1, R2. Here's R. Over here will be C. And because I'm just going to be making component values up, I have no idea at which frequency this thing is going to oscillate, so we might have to hunt to find the signal. I'm going to make this a 1K resistor. I'm going to make this a 4K resistor, just arbitrarily. Let's make this 10K. Let's make this 1 millifarad. And because I'm dealing with a capacitor, what I'm going to do here is I'm going to do dot IC. Actually, hold on. Let me label this node BC, just for the sake of argument. Let me label this node VREF, just so we can see what's going on. And let me label this node Vout, like so. And so I'm going to set the initial condition on my capacitor. So when we assumed how it was working, we said that our initial condition on our capacitor was that the voltage was 0, and we said VCC plus started out as Vout started out as VCC plus. Unfortunately, we can only specify the initial conditions on capacitor voltages and inductor currents in LT-Spice. So what I'm going to do to make this circuit work the way that I want it to is give my capacitor some small amount of energy to start with. So I'm going to say that the capacitor voltage at t is equal to 0 is going to be, let's say 1 millivolt. And what might happen is it'll take time for our system to swing up into full speed, but it'll start going here in a moment. So let's run this simulation. Let's do it for 1 second and then play around with stuff as needed. So what I'm going to do here is I'm going to add a plane, and I'm going to plot VC. So that doesn't look to be enough time. Down here, let me plot V out. Yeah, so I need to let it run for more than 1 millisecond. So let me make this 1 second. Still not long enough for it to really do things. Wait, sorry, I'm changing the wrong thing. That would help if I was changing the right thing. Let's see what happens in 100 seconds. Starting to swing. Maybe my capacitor, we'll just play around. Let's make it 1,000 seconds. Actually, let's not. Let's make this voltage larger and that'll effectively have the same result, or it should. Okay. So now when I give the capacitor more stored energy, we see that it starts to behave as we would expect. So the last thing that I'm going to do here is I'm going to add a trace onto this top graph where we can see Vref. And we can see that Vref effectively has the exact same shape as Vout. Vref ranges from 8 to -8, whereas Vout ranges from 10 to -10 because of the voltage divider that I've established, right? So 4/5 is 80%, which is why Vref is only 80% of Vout. But we can see that the capacitor voltage is chasing the reference voltage. And when they meet, so when the capacitor voltage meets the reference voltage, then our output voltage changes states and the cycle repeats. So we have developed a simple oscillator. Here it looks like, based on these component values, I'm just pulling up this thing here so I can see how long one cycle takes. So let's consider the cycle starting at 17.041 seconds. Let me get a calculator because I'm not going to remember this. So 17.045017. And then this cycle will end when we have the next vertical transition up. So somewhere around here, 60.7541. So it completes one cycle in roughly 43.7 seconds. So if I take the reciprocal of that, we have an oscillation at about 23 millihertz. Okay. So our conceptual analysis matched exactly what the simulation had. Now I'm going to give you guys some equations to explain how this thing works. Okay. So the period oscillation, so let me define that here. When it transitions from high to low, period is given by twice RC times the natural log of 1 plus beta over 1 minus beta, where beta is established by the ratio of R2 over R1 plus R2. So using the values that I used in the simulation, so beta would be 0.8. So 2 times R, so 10,000, times C, which was 1 millifarad, times the natural log of 1.8 divided by 0.2. Our period, according to our formula, should be 43.944 seconds. And I believe we calculated something, or simulated something very close to that. Just for the sake of argument, for when I ask you guys homework questions, the frequency is inversely related to the period of oscillations. Okay, so these are the three different positive feedback op-amp circuits that I expect you guys to understand how they work and all that kind of good stuff. You'll be asked questions about all three of these circuits in the homework set that's associated with this particular lecture. If you have any questions, I would be happy to answer them. If not, I will see you all on Monday.